자, 2020년 10월 31일 복합제 설계 수업 시작할게요. Well, today, October 31st, we will start our class today. We are supposed to take an exam, but we're gonna cover a little bit of a class and then followed by midterm. 수업을 조금 하고요. 그 다음에 midterm assignment를 할 겁니다. Again, if you have any questions, let me know either through KakaoTalk or chat, through chatting. Okay, today's class is very important for you to be able to do a midterm. So if you have any questions, do not hesitate. I will answer as much as I can. So that's a good way for you to well understand and prepare for midterm. Now let me ask, can you hear me well?
네, 잘 들립니다.
Thank you.
잘 들립니다.
Oops. Okay, first, not much theory will be covered, but as a continuation of our last class, Excel, we call high CLT. We like to continue to complete this worksheet. Well, this is the version we discussed last class. As a reminder, well, this is the ABD matrix, as you can see here, ABD matrix, and this is the graph showing OVX strain, OVX stress. Now, here, each column, oops. Okay, sorry. Now it's okay. So this is the Excel. We started last week, and as a reminder, this represents a load we are applying, and this represents in-plane strain and curvature. The in-plane strain is the, as shown here, any strain distribution of the laminate composite consists of in-plane strain and curvature. So as you can see, any strain in any ply can be represented by in-plane strain plus a curvature multiplied by its height. So as equation wise, this is the one. This is the how we calculate the OBX strain of any ply. So it's important. So input to this whole module is that this the load, in-plane load, and bending moment, and output of whole this CLT will be in-plane strain and curvatures. So the relations of this load and this in-plane strain and curvature is this ABD matrix. So as a matrix form, we can say N and M. These three components represent N and M multiplied by ABD matrix, this one, and epsilon 0 and curvature. Okay, so each term, N and M and everything is the has the three components. Okay, so how we calculate the ABD matrix? Now we have a Excel, and each row, each column represent a ply. So here, currently we have a column from 1 to up to 16 column, meaning 16 plies at this point. As we can see, I mean, we can easily add more column, more plies, or we can reduce the number of plies easily. We will show you later. Now, as is important, the format is that any cell in blue will represent input for users, and the any cells in black is just a processing values, and values in red will be output. Okay. Now we already cover all the theory and then all the procedures basically. And last week we just use a Excel address. Now today we're gonna change them and using the name. See, for example, any cell has the equations. Well, for example, this EX is a ply stiffness. EX is calculated by fiber stiffness, matrix stiffness, and fiber volume fraction, and matrix volume fractions. But as you can see, this equation is very difficult to understand, simply because this refer to absolute address of the Excel does not have any variable names. So we're gonna change that one. That's the what we're gonna do. Anyhow, I like to just remind you how the theory goes. The ZK and ZK1 is the positions of each ply, Z coordinates, and EX, EY, and so on is the ply engineering constant stiffness, and from this we define a 3x3 stiffness of the on axis. So its equation is like that. Again, we're going to change this equation using symbols. And once we have our own axis of stiffness, we can define the 5 invariant. Purpose of this invariant is to easily calculate all axis of stiffness, Q1, 2, 3, 4, 5, 6. Once we have this Q1, 2, 3, 4, 5, 6, we simply get the let me open the class note. Okay. Right. This is the equations to calculate the ABD matrix. Is simply integrations of all plies Q bar. Q bar is the off-axis stiffness, and this, as you can see, integrations now become the summations of each ply, and each ply, these integrations will give us the Q bar times the thickness, the coordinate, z directional coordinate. And Q bar, what is a Q bar? Well, is the off-axis stiffness, right? This is the key equations, and derivation of ABD. Of course, we obtain from the definition of the in-plane load N and M. N is the integration of the stress, and moment is the integration of the stress times the Z. And sigma bar is now defined as the off-axis and off-axis strain, and put it here. And there, epsilon bar is what? Off-axis strain, which is represented by the in-plane strain plus the curvature. Okay, so this slide I will simply copy to here, and then I will also copy the definition of ABD matrix here. Okay. So the equation, the theory is clear. Again, the definition of in-plane strain and definition of a moment and definition of a sigma bar. Sigma bar is the off-axis stiffness, the stress, and Q bar and epsilon bar. Here, the most important point is that epsilon bar, what is the epsilon bar? Epsilon bar is given as the a in-plane strain plus the curvature. That is kind of assumptions in most of our structures. In most of the structures, which is relatively thin through the thickness, will follow this behavior. I mean, assumptions represented by this assumption. Strain is a linearly distribute through the thickness. This is very important observations and quite well catch the behavior of this strain. Okay, that's so we put this equation to here. So this epsilon bar goes to here, and this sigma bar goes to here, and then A and B and B and D, because the epsilon 0 and K is the unknown we like to obtain. And then this is now defined as the ABD matrix. And simply ABD matrix now can be calculated by the summation. So again, N and M, this is the load we will be given. We will specify a in-plane load and bending. Output or unknown will be epsilon 0 and curvature, right? So that's why we simply have this ABD matrix, right? And again, this ABD matrix is the most important a core stiffness in laminate composite, and most of Abacus and ANSYS, all the CA tools are using this theory and this process, especially for shear element. The shear element is the a layered element, layered of all the plies. So it's so important. Okay. So anyhow, we have the OB-axis Q1, 2, 5, 6 here. Q bar is this guy, Q bar, right? This 1, 2, 3, 4, 5, 6. We have this actually 9 component, 3 by 3, but this is a symmetric. So we're gonna just calculate. Sorry, this is a sigma 1 to 6, not the 3. Sorry, it's not. It's a mistake. Has to be 6 and has to be epsilon 6, not the 3. Okay. So we have a Q1, 1, 1, 2, and 2, 2, and 1, 6, and 2, 6, and 6, 6. So we have a 6 terms, and we have equations, which is calculated from calculate from a Q. And rather than calculations, calculating directly from Q, we define the invariant, okay? And that's relatively easier in programming and give us better accuracy. Not so much important, but this is how we calculate. Okay, so once we have an ABD matrix, ABD for each ply. I mean, each ply means that, you know, as you can see here, A has the summation of this guy, this term, and this term now is represented by this. As you can see, this C61 is the Q11, right? And C44 and 30 is the a coordinate, two positions. I like to, for those who don't have an idea about the Z, I will just copy this one. The Z is again the coordinate, okay, Z coordinate. At the very bottom, we have a Z1, 2, 3, 4, 5, and so on. And each ply, we just call the bottom one is the ZK, and top is the ZK1. And the second ply also ZK1, ZK and ZK1, and so on. So ZK means that the coordinate of the bottom ply, bottom surface, and ZK1 is the top. So is clear from this figure. Okay, so that way we calculate all the ABD matrix. Now we have to sum them up, right? We have each ply, we have the summation from n to 1 to n ply. So that's why at the very last column we have a summations, okay, summations of all the plies, which give us a B matrix and A matrix and B matrix and D matrix. Again, just for the purpose of easy format, we just display 6 components as a column. As you can see here, A is actually 3 by 3 matrix, and 3 by 3 matrix like a Q. See, this is the A matrix equation, A matrix and Q matrix, and this is just a scalar multiplied by every terms. So this one is just we expanded to a column like that, okay, like this, and 1, 2, 1, 2, this. We have 6 terms. A is the same thing, and B and D are all the same thing. So a theory is consistent and format is consistent. We just follow this consistency. Okay, now as I mentioned, if you click any cells, the equations rather complicate. We cannot even understand what it means, which is not so good. And simply because we follow, we just use the Excel address, which is not convenient at all. So I highly recommend don't ever use this kind of Excel address, C45, where is the C45 and this, and well, it represents some color, so you can barely see what which one is which, but this way you cannot find any bug, if any. Okay, so it's very, it's not so good. So I will show you how to use a symbol-like, programming-like Excel worksheet coding. Okay, so here, this is the, we define the total thickness. This is the one cell address, right? One cell address. But this one is the what? A vector. We can call vector because this is the a range rather than not just one cell. So this is a range. So each range has the name like a ply thickness, and this range has the name of the theta, and this range also will have a name. Okay, to be consistent, I'm gonna delete this guy. Okay, I'm gonna delete this guy as well. Just ready to assign the name. This first column will be the name for whole range. So make sure everything is ready. Okay, and then now we select everything. We select here, okay, this much, including this first first cell, and then go to formula and create from selections. It automatically detects where the name can be, and left column say okay. Okay. Now the ply thickness, now this much range, excluding first one, this much range will have a name called ply thickness automatically. And let's do it again. You want to give a name as this one, as a theta, you go to formula and you go to select create from selections and left column, it automatically give a name. So this much range, not the first one, okay? This much range will automatically has a name theta. So you know what the name will be for each range. You don't have to do a one by one. You just select every cell, whole range, and then go and select, and it says left column, just to say okay. This one, because we already had some definition in, okay, so we already defined some names here in the previous class. I will cover that one later, okay? But anyhow, now as you can see, each a row now has the name as first column, right? Okay, so it's very convenient to assign name. Not easy, not difficult at all. Now, this ZK and ZK1 has the, and this one has the little bit of an exception, but this one ZK, as you know, the bottom ply, bottom surface, and this one has the, what? As you can see, ply thickness plus a bottom ply, bottom surface, obviously, right? ZK1 will be, let me write down. Okay, just 1 second. Oops. Okay. Okay. I would just like to just remind you that okay, remind you how we calculate this one. Well, this is not difficult at all. See each ply, say each ply, we have this is the this is a case ply, okay, arbitrary case ply. This is called ZK, and this is the ZK1. We just gave a name like this. And then ZK1 is simply what? ZK plus, let's say this is the A thickness, thickness is given as here, ply thickness, as you can see here, ply thickness. So this is a simply ply thickness, let's say H, okay, HK. So say this is the HK. So HK is the ply thickness. So now, very importantly, this one, again, simply ZK plus ply thickness. But again, we're gonna change this name as here, equal ZK, right? And plus ply thickness and enter. Okay, well, the reason is that, well, this is a little bit exceptions, and the let me, okay, let me, okay, let me do it again, okay? Sorry. Well, this is a little bit new feature of Excel. So I want to be very careful. So this is the a total thickness, because the very bottom, let's say we have many ply like this and like that, and so many ply. At the very beginning, this coordinate Z1 will be simply total thickness T minus half, right? And top is simply, I mean, T over half, and the bottom will be half minus, right? So that's a starting point. Anyhow, here the equation will be simply like ZK plus ply thickness. Now, importantly, ZK already defined as the what? Range, right? This is GK as the defined as a range, and ply thickness has the definition of a range. And then if you just enter like that, the whole range will be automatically entered, as you can see here. And here, this one is actually this guy. But as you can see, this is the defined as the range. It cannot perform. Well, this is very exception. I don't want to confuse you, but unfortunately, this is the and this one. C44. Let me see. And this and that. Well, I have to, sorry, this is the exceptions. And now the difference between this at sign, okay, at sign is just represent to one cell rather than range. Well, this ZK is the little exception. I will come back to this one, but I don't want to confuse you. Here, importantly, these things, EX, right? EX, what does it mean? EX means C25. C25 is EXF. So basically, this is the EXF. EXF. And C40, what is a C40? Is a VF. And C32. And one thing you need to be careful is that, you know, sometimes the name is defined here, and also you define some name here as well. We already have a name somewhere here, right? And then you need to clarify which VF you like to refer to. Okay, so that's why we need to be careful. And okay, let me continue. So VF, and now okay, well, I just like to just for the clarity, I'm gonna delete this guy. Okay, I'm gonna delete this first micromechanics, because all the equation is already in the main CLT. I'm gonna delete this, and then well, we're gonna correct that. So here, let me correct this EYM, basically EXM, which we already have it, and then just enter. Equal EXM. And as you can see, when I enter this one, EXM is defined as a range, so automatically fill whole range, okay? And if we want to just enter only one cell with a name, you only need to do is just enter at sign, okay? Then this will represent only this guy. And in that case, you need to copy everything for this range. Then each one will represent each corresponding value. but in this case, we just use the EXM. To do so, you need to be make sure everything has to be 0. Then EXM enter automatically fill whole range. Okay, and this one, as I said, that's why we need to have a add sign here, and this and so on. Okay. Now, oops. Here, EX, now, as you can see, VF now is only one VF. And what is a C32? C32 is the EXM. So EXM times C41. What is a C41? Is a VM, right? Well, I need to clear them all. It's automatically filled. And we're gonna do it. I'm gonna delete whole this part except the first one because we don't wanna delete the equations. And here C40. What is a C40? C40 is simply VF. This guy is the VF. And well, again, the VF has the two definitions. One is the workbook and the other one is the worksheet. Now you go to a name and the VF, as you can see, this guy has been defined in the worksheet, which I just delete. So you don't need this one. We just get rid of the old cells. And now, very importantly, this is the referring part, and this is the just value. But you need to be careful about the scope. Scope means that this guy, Q66, defined in the range, scope is the only this worksheet. And let's say VX now has a scope as a workbook. Book means the whole worksheet, right? And the that's the one you need to be careful. So some name are the confined to scope of the main CLT, and some are defined for whole range. So it's automatically assigned depending on when you assign the name. Okay. So let's say we have EX and this. Q40 is what? A VF. Now we have only one VF. C26. What is a C26? Well, C26 is the EFY. And C41 is the VM. And C33 is the EYM. And enter. Sorry, this one has the wrong name. As you can see here, EYF, right? EYF. So in Excel, when you program, you cannot mistake. It automatically give us the so again, when you enter this one, is automatically the ranges are filled with the same value. And let's do it. Let's continue. Vx, I'm sorry, mu x is the C27. What is a C27? VPX and C40 is what? VF, and C34 is the VPM, and C41 is the VM. F, okay. Right? And then, well, this is not that much. We can just do it. EX is the what? ES, C40, VF, and C28, ESF, and C41. What is a C41? Well, VF, and C35 is ESM. Now, as you can see, when you see this equation, it's very clear, right? Very clear, and it has all the symbols. And we do same. C45. What is C45? Well, this one is the EX47 is mu x, and C46 EY, and C45 EX. C46 EY, C47 X, C46 EY, and C45 is EX. Okay, and then like that. Now, as you can see, this one is kind of repeating. So I'm going to copy these terms and this. And C47 is UX, and 46 is the EY. And then divide by this guy. Okay, and QS is simply ES. Okay, U1, I'm gonna just select like that, and then I'm gonna replace, because C50 will be replaced by the QXX. Let's replace all. And 51, C51 is the QYY. and 52 XY and 53 will be SS. Okay, so double check everything is now well changed. Again, I'd like to emphasize the definition of invariant now is just clear, very clear from that the names, right? And while we do the same thing, because Q 1 through 6 are defined from U, we're gonna just replace a C55 with what? That's gonna be U1. And C6 will be a 2. And 7 will be 3. 8 will be 4. And 9 will be 5. Up. U4. Want to check. Yeah, I made a mistake. Huh? C58 to U4. Okay. And then what is a C23? Huh? What is a C23? C23 should be theta, right? Where is a theta? Okay, theta is here. So okay, now everything is in terms of symbols, and A11 and so on. Again, this one is the Q11, right? And C44 and C43 is simply what? That's a Z coordinate, ZK1 and ZK. So this will be simply a Q11, and this is a ZK1 minus ZK, oops, ZK. And this one, I'm sure will be the same. Just replace this is the 1, 2. As you can see now how simple it is. The programming is nothing but just exactly same as the theory, we just type in and then we can see how to make mistake. The same thing here. So I'm going to select them. So I'm going to use this one. And then secure, and divide by 2, right? Actually, this is all the same terms. I could have defined this as another variable, but okay. Okay, so you can see how easily we could have done. Well, we could have done last class, but I just like to make sure the all the Excel functions, and now you can see how convenient it is. Now let's continue. Okay, let's continue. See last class, and epsilon 1 to 6. Okay, so this one, epsilon 1, I mean the in-plane strain, and zk. What is this one? Well, this is simply zk. Okay, also this is the azk, and this is the zk, and the now this is the top surface, so this will be zk1, right? And this will be a zk1, and this will be a zk1. And the O-axis strain is the angle transformations, and C61, 63, 63 is the this one, the O-axis stiffness, I mean the stress is simply this guy. C61 is what? 61 is the well, Q11. Now we we can easily follow the this one has to be epsilon 1. See what it is simply as shown here, sigma 1 bar equal this first row times this 3 component. So Q1 times epsilon 1 plus Q1 2 times epsilon 2 and plus Q1 3 multiply E3, right? So this is just, so we can simply do like plus like that, and this gonna be 1, 2, and this gonna be a 2, and plus, so this gonna be a 1, 6, be careful, 6, not the 3, and this gonna be a 6, right? So enter. And this one, we just simply copy, but this gonna be what, 1, 2, and 1, and this gonna be a 2, 2, and this gonna be a 2, 6, right? And this one, I'm gonna copy, and this gonna be what, 1, 6, right? And this gonna be a 2, 6, and this gonna be a 6, 6, right? And this, oh, sorry. See, this one is a ZK, sorry, mistake. So this is a strain at the ZK. This is a strain at the ZK1. So we need to do, okay, we need to ZK epsilon 1 times, this is the, at ZK, the K, I'm going to change the name because the K, and this is the K. And this is going to be a K1, and this is going to be a K1, and this is going to be a K1. Well, the reason, okay, the reason why we have say we have a ply like that, and each ply will have a strain. Well, we may have a strains like say something like that, right? This is a ply, and this is the a strain epsilon bar, and this can be a strain like this. And now the K ply will have a strain this much and that much. So this is the a case ply. And again, the bottom and top, this is a ZK, and this is a ZK1. And each ply, and this case ply, may have a strain at the bottom and strain at the top. And of course, we do the same. This K plus 1, we have this strain and that strain. Where strain is continuous, so we don't have to actually define a top and bottom because they are continuous. But the reason we do this is simply because because of a stress. Stress, as you can see, at each ply, right? Each ply. This may have a very much discontinuous. This can be a very much discontinuous sigma bar, all axis, very important. Why? because sigma bar is multiply q bar epsilon bar. Epsilon bar is the continuous through the thickness, but this q bar at k can be different from each ply. This is a q bar and q bar. They can be all different stiffness, right? So each ply, top and bottom can have a different stress. Here is the stress is this much, and here is this much stress. Again, the upper one can have this different stress like that. So that's why each ply, okay, each ply we should have a two value, bottom, top, and stress bottom, top of each ply. Okay, it's very important. That's why we so far again every ply we just have a Q, we just have I would say we had a Young's modulus, we had a Q, we had a U, and you had a Q bar, and we had each ply A. But the strain and stress wise, we need to have a top and bottom. Okay, it's important. So I'm gonna have this one as the I'm gonna change the name. This is gonna be a K, and this gonna be a K, and this gonna be a K. And stress will be this gonna be K, and this gonna be a K, and this gonna be also K. Now I'm gonna redefine as this much as the given name. Okay, and then we redefine here Q sigma 1 K is the we have to, oops, sorry, this one has to K1. I'm gonna redefine. So this one now Q11 times, as you can see, Q11, I mean Q times epsilon. Epsilon has to be same positions. So this needs to be a K, right? And this one has to be, oops, 1K. And this one has to be a 2K. And this gonna be a K, right? Okay. And the this one is the same thing, K. And K. Okay, so K. Okay, now I will just copy and paste this one. But here, instead of a K, we're gonna replace instead of what? Instead of K, we replace with a K1. Okay, so everything is the well done, and I just want to say we could have done this way last week, and as you can see how easy we can program. And if you see formulas, I just want to show you the formulas we entered, and as you can see, all the formula Okay, all the formula is exactly same as the theory we covered. While sometimes you need to double check, but very easy to follow and hard to make mistake, right? Hard to make a mistake. And when you program, the naming needs to be very consistent, then very easy to correct them and find the bug. The programming is the not just a programming. Program has to be, considered for next maintenance. Maintenance is the a point of the programming. Okay, so everything looks good. Okay, so I'm gonna save this, give a version 4. Give a version 4. But don't forget, we had previously we had a micromechanics. Okay, micromechanics. I just make it simple for you, but we will need to use this one to calculation of a strength. Okay, that strength terms will be a program next time. So keep that in mind. So anyhow, this is the just a CLT, and the I will move at the very first worksheet and some give a the color. Okay, so again, you're gonna keep updating this worksheet and workbook, high CLT, and this is gonna be your own tool for your research. I'm sure this is gonna be very useful. Okay, well, let's take a break, and then break. It is 2:23. Let's come back 2:40. Okay, 2:40. 자, 2시 40분에 다시 시작합시다. 오케이. Okay. Let's continue our class. We will complete a little more derivations in this class. You may wonder what is a midterm, but don't worry, I will assign you. Okay, so just follow and pay attention to what we are doing now. What's the definition of this in-plane O-axis strain and O-axis stress? And if we go back to our lecture notes, like to let you know where we are. Basically, we are at here. Once we have an ABD matrix, and this is the in-plane O-axis strain, we're gonna plot like that. So basically what we are doing now is these calculations, strain. Okay, I'm going to copy this one into our Excel. Actually, this is the one we are trying to program here. See, we got all this strain. I mean, the strain of the x-axis strain at each ply, and bottom and top. That's why we have a K and K plus K1. And then a Q, I mean the sigma bar. To calculate the sigma bar of axis, we just multiply the Q bar. So as you can see, we just multiply Q bar for each term, right? So no problem so far. But now what will be the next one? Next is simply to get the on-axis stress, okay, which is the very important. I'm gonna put it here. So again, we have off-axis stress or off-axis strain. Now what we like to do is the on-axis stress. Again, each ply has the different angle. To calculate the on-axis stress, we have to rotate or transform the stress into an on-axis by theta. All we need to do is simply to multiply transformation matrix T sigma. This is the equation we have. T sigma and plus direction. Plus means a plus rotations, and we already have that. Let's go back to that transformation matrix. Okay, here is the transformation matrix. Transformation matrix is simply, this sigma. Okay, I'm gonna copy this and paste to here. So I'm gonna write down here. These are all off-axis. Now we are, I'm gonna just say, I'm gonna give a format. Off-axis strain, and here is the off-axis stress, right? Now I'm gonna give them a box. And same here. Now, what we like to do is to calculate on-axis stress. Well, how to do that? This is the equations, and then we simply, we don't need any equation. we're gonna delete this, and now the symbols we're gonna define as instead of 1, we're gonna use X, Y, S to represent the on axis. Y and S. Okay. This is the Y. Okay, so this one also is gonna be X, and this gonna be, oops, a Y and S. And then let's give a name. Okay, to transform, what you need to do is the multiply. M is the cosine, right? N is the sine. So this one will be simply follow this. Okay, equal stress 1K times cos radians and theta and square. Let me see, it works. Okay. Now that is the cosine, and we also need to have a sine. The second terms plus, and this is gonna be a second, right? Sigma 2, and n is the sine. And sigma 3 is, we define as a 6, and this sine and cosine. And cosine, right? So okay, there was a typo here, so it's automatically corrected. Now we have a copy, and what needs to be changed? Well, this one, we, instead of a cosine, this is gonna be a sine, and this is gonna be a cosine, and this is gonna be a minus. Well, as long as you completely understand the theory, the programming in Excel is very much straightforward. And here is the K1. K1 is the top surface. So K1, all you need to do is just replace like that. So this is the is OX now on axis stress, right? On axis stress. In here, let's also calculate the on axis strain. On axis strain. On axis strain. And So instead of stress, we're gonna change it to epsilon. And also here, first we give a name, okay? And here, see what needs to be. Okay, let's try to find the theory, I mean the strain transformation matrix. Okay, copy and come back here. Okay, so now, as we already know, there's symbol, I mean, the transformation is a little different, slightly different. First, let's change the, instead of str, stress is, let's replace with epsilon, no problem. And then instead of, cause this, everything is will be the same, but except that there won't be, oops. Oh, sorry, here we have a 2. So we have to 2, right? And also we have a twice here. And also here, well, big mistake here. Here, M and N. Times, okay, M and N times sigma 1, sigma 1 minus sigma 2, right? Sigma 2, and this is the plus. No, sigma 1, this has to be minus, and this has to be a plus, right? We are following these equations. I made a mistake. What is this? Right. And then plus and square minus and square sine and what times stress a sigma 6k, right? Okay, we don't want to make any mistake. Double check. Okay, cosine square. Okay. So these terms, okay, correct. I'm going to do it again here and this and replace k with k1. Right. Now here, replace as stress, replace with epsilon. Now we had to change a little bit here. We don't have a 2 here. We don't have a 2 here. And now here we need to have a twice here. Okay. 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 And okay. We do the same for at K1. We don't have a twice here. We don't have a twice here. And we have a 2 here. Okay. Got it. Okay. Well, what we have done so far is to calculate all axis strain stress and all axis stress strain. And please remember that how to calculate the own axis. Own axis, we just a transform. Please, transform means that this one, you know, all these strains are stresses. This is the you know, this is the all axis, and the same as the loading direction, and this is the own axis, right? This is the own axis, and this is the fiber directions. And between them, we have an angle theta for each ply, okay, each ply. Okay, now at this point, we like to plot them. We can simply plot like that, but this looks not so beautiful because this only plot at the bottom. We like to plot like, you know, each top and bottom, I mean, bottom, top, bottom, top, bottom, top, bottom, top. We don't want to plot just bottom, bottom, bottom. That's why it doesn't look good. We need to plot every 2 bottom, top at each ply. So to do that, let's define a new cell, new range. Off axis or on axis. What do you mean by the same? We are using the different rules. I mean, this is the on axis. I mean, off axis and on axis. This is the off axis, and this is the on axis. They are same. I mean, the different strain and strain, the stress and strain, they are a little bit different. But what do you mean by the same? I think that in the derivations, right? In the derivation, we use all the transformation. Yes, of course, they are the same as the one we used. Okay, of course, they are same as the one we used in the derivation. Okay, that's a good questions. Now, again, to plot this, let me, each ply, we have a top and bottom. So the strategy is that at each ply, first ply and second ply and third ply, we're gonna give a column-wise space, okay? Column-wise space, and each one we have a 2, and top and bottom, and so on. So I would say this one will be this plus 1, and just copy and paste. So far we have a 16 ply. The reason I like to plot in column is to make look nice. We only have a 16 ply at this point. Okay, so what I'm trying to do is that this is the ply, 1 ply, top and bottom, and so on. So this is the, I would say, coordinate, okay? This is gonna be a Z coordinate. Z coordinate means that, okay, this is the AZ, K, a component, you can say component, index, ZK, the first component. And this is the how we get the value, okay? ZK index means the component number. This is the first component, and that will be the bottom. And then this one, I would say, this is a ZK1. So here, the first ply has the bottom and top, but same ply number, same, this is the a ply number. We intentionally give a 2 value for each ply because of bottom and top, right? So we just copy and paste. So as you can see, at the each one will have a same coordinate. This is a Z coordinate. Now, what we like to do is let's call a O-axis stress. Say O-axis strain first. O-axis strain. I will just call O strain. O-axis strain. And first column, I would say 1, 2, 6. O-axis strain. And to do that, you need to do is the just call index the strain, right? And 1, and the this is the see the bottom, so will be K, comma, and this guy, right? And this will be just 96. So this is the how we record, how we call this value. And then the next one will be the same one, but ZK1. Because each ply we have a top and bottom, right? Here is the a top surface and like that, right? ZK1. Okay, ZK1. Oh, sorry. Has to be this guy. Sorry, I made a mistake. This one has to be this guy. Okay, so first the strain, strain 1 and bottom. To refer to bottom, you need first apply. And same, but this is a K1 top. And then just all you need to do is just copy and paste it here. And same thing. I'm gonna keep this W. And then this is gonna be a second term, bottom and top, right? And also this gonna be a third term. I mean 6 and 6. Okay. So we can copy and paste. So as you can see, we have a strain. And just for the purpose to show you, now you can see the strain can be pretty much smooth. Sorry, something is not right. The first apply this, and that second apply, this has to be same. K1, okay, so let me double check here. Oh no. Oh. I don't know what I'm doing here, man. I'm sorry, it has to be a strain, right? So all the epsilon and copy and paste. Now the strain, OBEX is a strain, has to be, let's plot them. Oops. Now, as you can see, the obviously the strain has to be continuous like that. Now we do same thing for O-axis stress. Right, O-axis stress. And here, replace epsilon to stress. Right? And then also I like to plot on axis stress okay, on axis stress. Here what we need to do is that change 1 to x and 2 to y and 6 to s. Okay, so can say this is x, y, and s. Okay, and now I'm gonna move here and copy strain here. Oops. Here the on axis on axis strain, and here instead of we already changed here, instead of 6 replace and 2 to y and 1 to x. Okay, so epsilon x, good, y in k1 and x. Okay. Now it's always important to visualize all the results using the graph. So it's worthwhile to spend time to make this table for plotting, and the and this is the stress. As you can see, is pretty much discontinuous. And so this is the O-axis stress, and this is the off-axis strain. And this one, let's plot this and this, and insert. And this is what? On axis strain. On axis strain. The reason, obviously, they are pretty much a discontinuous simply because we have a different angle. Now this, and then on axis stress, 3 component, each ply, and insert. Okay, so this one, simply we have a on axis stress. Okay, and here well, I'm gonna change a little bit for the lesson here. Okay. I'm trying to off-axis stress. Right. Just copy to here to there, and then replace off to on. So that now we have a legend on axis X, on axis Y, and so on. Okay, we can have them in a separate, let's call our plot. And here we just copy, and then let's see, off-axis starting from off-axis strain. Remember, we theory-wise start the off-axis strain multiplied by stiffness, off-axis stress, and this is the on-axis strain, and this is the on-axis stress. Right? Okay, so this is the output as well for each ply. And okay, so let's try to have a new window. Let me see. I need to close this, and arrange like verticals. This is the same worksheet, same workbook, but just a different window. And here I like to show you how we change this plot. The first, let's change the angle rather than we just change everything as the all 0 degree. Imagine we layered all the 0 degree, okay, 0 degree, and we apply, this is the load we apply. This is the load we apply. And now we apply the moment, but let's apply just in plane load, okay? Just in plane load, x-axis. Let me see. Okay, so off axis, and very important, this is the just off axis, I mean load we apply. We just load applied as the N1, like that. This is all 0 degree layer, as you can see, all 0 degree, right? All 0 degree. And what happened is that, first of all, off-axis strain, off-axis strain, what will happen? Well, what will happen is that this guy will expand, but at the same time, it will shrink this much, right? So this shrink will be exactly same amount as the on-axis property. But anyhow, what is this? This is the off-axis strain 1. 1 means this much extension. And 2 is the shrink. That's why we have a negative. Again, this is the all ply, okay, all ply. This is a ply 1 and ply 2 and ply 3 and ply up to 16. We have all the same. And there's a no shear strain. That's why shear is 0, right? Now the stress-wise, okay, stress-wise, since we apply this only N1, stress will be only this one, and the stress here will be all 0, right? No stress. So we have an off-axis, only off-axis sigma 1, as other sigma 2 and sigma 6 will be 0. And on-axis strain, pay attention, they will be exactly the same. Why? Because all 0 degree. On-axis stress will be the same as the off-axis because again it's all 0 degree, right? Now let's play with this load and play with this angle, and now you can better understand the composite behavior. Say you applied N1 and N and at all direction same amount, okay? Same amount of the strain. See, this is a 0 degree, and 0 degree, I'm gonna get rid of this. 0 degree, and apply the same, okay, I'm gonna apply a Y direction. Okay, Y directions, similar behavior, but pretty much small. What we apply is like here, all 0 degree. Now we apply this much. So we have a epsilon 2, but epsilon 1 is really small. Why? Because the Poisson's ratio is very small. So there is a shrink, but very small, because this is the fiber directions. Okay, that's why you remember this small blue, the line blue is very small. And this is epsilon 2. And you can play with 1, 1, and also you can play with, say, moment like this. Okay, what is going on in the moment? Moment is that like this, okay? Say we have a plate like that, all 0 degree, and then we apply the moment like that. This is the M1. Now, obviously, this is gonna be a band like that, right? So at the top means this ply. Okay, this is the a top and bottom and bottom, and you have this much tension, and the bottom you have this much compression. But how about the epsilon 2? Epsilon 2 is the negative. How come it's a negative? Well, this is the called anti-curvature. Oops. This is gonna bend like that, okay? So in plate, laminate, when we have a bending like that, bending in this way, right? It bending this way, but in this direction, we're gonna have a slight anti-curvature. And here is the like a beam theory, we have a R, but this curvature, we have another R. This is the RY and this is RX. So this is the structural behavior. That's why we have this much, a little bit less than this one, and the on-axis, off-axis the same, right? It's very important behavior. And this is the, again, 0 degree anisotropic property. And now, if we apply the layup, like I would say, what angle you want to try? You want to try all 45, or just 45, okay? Let's see what's happening. All 45. And then let's say we apply only extension. Let's see what's happening. What's happening here, importantly, now we, again, we have just a 45 and apply load, right? Then this gonna be a extend. This gonna be extend, but at the same time, this gonna be, of course, a shrink, but importantly, we gonna have a shear strain. You know, the angle will change, shear strain, because 45 is not the balanced. That's why we have this much off-axis strain-wise, this much epsilon 1 and this much epsilon 2. And as you can see, you have a shear strain, non-zero shear strain, right? Non-zero shear strain. And now, what if we apply plus 45 and minus 45 and so on? Just repeat, a plus 45 and minus 45 and repeat, just alternating. Sorry, it's a little dirty here. The strain wise, now plus minus, so on. Okay, plus minus. Let's say we have a plus, minus, and plus and minus. So thickness wise, we have a plus 45 and minus 45 and plus 45 and minus 45 and so on. So under extension, we have a same, we have a N1, okay? We have a N1, and we're gonna have a extensions. Of course, we're gonna have a extension in one directions. We apply load here. We're gonna expansion. We're gonna have a shrink, right? And we don't have any no shear strain because plus minus all balanced, okay, all balanced. But they are not quite perfect. I mean, there will be a slight curvature. See, there is a slight curvature, but we're gonna cover more next week. But the most important point is that this gives us all the details: stress, strain, and off-axis and on-axis. And one thing very important. Now we are getting close to a midterm. Here, on-axis stress is the, let's say each ply, we have a fiber. This is a fiber strain and fiber stress, right? This is the fiber directional strain. This is the on-axis strain, epsilon x. That is this guy. Stress and strain. Okay, this is a fiber directional load. I'm gonna get rid of this. Okay. Now we already have a quick chart. Okay, quick chart is the one, the macro. For that purpose, you need to define a range. You can define the range. This is an important step. Range defined as the quick chart. Okay, you have to have a name like a quick chart. This is the output. Oops. Quick chart. And first one is the name of the worksheet. I will call just output. And then this is the output. And this is gonna be an input. And let's say this is the output wise, the epsilon, x. I would say epsilon x is the fiber directional, and the first ply. Okay. Okay, before that, we like to have a epsilon, the in-plane strain, and the first one, in-plane strain. And in-plane strain, where is the in-plane strain? And this one equal this guy. And input, now we like to have an angle, like an angle like that. And so this gonna be a angle as input. And this gonna be, say, same as that one. So this is just one example. Okay, this is just one example. Every ply will have the same angle. Now you can change, enter this angle, like a 10 degree. You can see here, 10 degree. Now this output will be automatically calculated. I will show you. This one has the dependency. It goes there, and then you know, all kinds of a calculation. And this guy comes from from here, right? Go there, and all the calculation and output will become here. And so we can also calculate. You can do any variables, basically. Let's say 2. This means epsilon 2. And you can define anything, except the first one will be the play as the input. Now, as the quick chart, you click, and this is the initial value of the input. Say angle will be 0 degree to 90 degree, and every step, every degree, 1 degree, and click OK. Oops. Sorry. In fact, I changed a little bit of. I'm gonna delete. Let me see. This is the 0 to 90, and what is the current worksheet? Current worksheet has to be. Well, before class, I changed a little bit, and I didn't confirm. Sorry, I need to quick chart and output. Okay. Don't understand. Why key chart? Key chart. I don't get it. Let me key chart. Okay. I'd like to maybe some I don't understand. We have this value. Oh no. Very strange. Well, this kick chart worked the last time, but I don't know what changed the inside. Well, this is an important step. I mean, the last step to assign the midterm. So I need to go through that. First of all, let me okay, I'm gonna just show the output of this kick chart, but without you know any chart. I'm gonna charting is not so important. The point is that okay, here we define this a range called quick chart. Okay, this is important step, and you have a macro. And here, this is the one, I'm gonna get rid of this. Here, the output is the a name for new worksheet, which will have all the output of this. And as you can see, this dialog box asking for what's the initial value of this input. Input is the right now, this input is related to angle. So I will change it 0 to 90 every 1 degree, and then okay. Then the output, see, output worksheet has been generated from this. Output is named here, and the variable is these two result that comes from here. And as you can see, this one is the input, in this case the angle, and all the output is the calculated. So we had some problem with plotting, but we can manually plot them. And as you can see, this is the epsilon 1 and epsilon 2. What is the x-axis? In this case, x-axis was the ply angle, right? Ply angle. Okay, so as you can see, 0 to up to 90 degree. As you can see, how strength is changing. Okay, how strength is changing. And of course, you can see ply strain. Okay, this is the ply strain, on-axis strain, and epsilon x and epsilon x k1. let's say you like to calculate maximum epsilon x is a fiber directional stress at K. This will be the maximum, right? This is the maximum fiber directional strain in all ply, and including top and bottom, you can add simply at the top and bottom, right? Maximum. See epsilon, this guy, this one, and this one is all top and bottom. The point is that, okay, I'm gonna put it here. This is the maximum on axis strain in fiber directions. Okay, so let's say instead of this variable, we like to have a maximum on-axis fiber directional strain. And value will be as output. Now, what we like to do is that let's try to plot and then see. And this is the plot we have. This, we're not gonna have this. And this one is the maximum on-axis strain in fiber direction. When we have a 0 degree and the given load, the fiber directional strain will change like that, right? And for the layup, like all UD, all same angle, and all the in-plane load 1, okay, in-plane load 1. And if we have and different load 1 and 2, and maximum strain is the this one again. Now angle, like to say we like to have a plus minus, like a plus minus. And this and that and this and that. So we, as you can see, if we have an angle here, then this is gonna be automatically plus minus, etc. And for the given load 1 to 2. And this will be the output as the maximum the strain, maximum fiber directional strain. Let's see what's happening and all the angles. And as you can see, certain angle, some strain is reaches the maximum. Some angle, what angle will be? Well, something like 50 degree. What it means is that, let's say this layup sequence, as you can see, is the all plus, minus, and plus and minus. And load is the N1 equal 1 and N2 equal 2. And again, if you like to change a certain angle, and this will be automatically plus minus, and this value will give us automatically the maximum strain, right? maximum fiber directional strain. In other words, a certain ply and fiber directional strain. This is the fiber directional strain. This is the epsilon x. And we have a plus and also a minus. We have this fiber directional stress, and we have a maximum of the fiber directional strain. So an angle is again plus or minus theta, and theta is ranging 0 to 90 degree, right? All the angles, and then a load is given like that, and then what will be the maximum strain? Okay, maximum strain. And as you can see, maximum strain, we can easily see around 50 degree, around 50 degree. 50 degree means, I'm gonna plot them. 50 means a little bit of little bit more than 45, right? So let's say this is the N1 and N2. N2 is the twice and N1 is the 1. So when we have this fiber as the, see this one is the plus and minus 50, this a strain will reach the maximum, will reach the maximum, and that's the how we can carry the load. Okay, this is the one example. Again, now the midterm I will assign through a cutoff, and then here you can use this macro, and then you can change this variable. Again, this is the a variable, and this gonna be a output, and this comes from as you can see, this comes from here, and that comes from here, right? And again, this one doesn't have to be this one value. You can define any value you like to have. Sometimes you like to have a transverse, say on axis, a transverse. Transverse means what? Instead of y, you can define x, you can define y, right? Okay, so I just like to emphasize that how much you can do with this worksheet and the HYCLT. You can do a lot, and I just like to give this one to you, okay, for you to do some midterm. And I will save. We had a little problem with the plotting, but don't worry, that's not the major one. We can just keep, we can easily modify, but currently it's okay. And this is again the output of this, all the strain and stresses, and this is the output from quick charts. Okay, so our midterm I will assign through a our Kakao group, and you submit your midterm in each submission, your own submission cutoff. Okay. 이 수업 끝나자마자 midterm을 어사인을 할 겁니다. 제가 이 워크시트는 여러분들한테 공유를 할 것이고, 숙제를 내주면은 이것을 활용을 해서 각자 midterm을 제출을 하도록 하세요. 제출할 때는 그 복합재료 과제 자기가 보내는 데다가 보내주시면 되겠어요. 오케이? Is there any question? Sorry, it's a little bit over 4 o'clock, but I had to reach this point. Okay, so again, if you have any question, you can ask. You can ask in the Katalog. I will reply as much as I can. Okay, so that's the end of this class. Thank you.